have done it. We have finally arrived at the very last textbook lesson of this school year. We're on Module 11, Lesson 5, which covers assessing visual overlap. The textbook even gives us a promise that this is going to be a super short lesson, a single day lesson. There's only 5 resources, folks. Let's get this thing done. During a recent Summer Olympic Games, the United States sent 269 female athletes, including a 16-member field hockey team and a 13-member water polo team. Suppose the heights of these Olympic athletes were sampled and the results were recorded. The table shows the heights in interest of the 16 female field hockey athletes and the 13 female water polo athletes. The table also gives the mean height for each sport and the mean absolute deviation in inches. What do you notice about the heights of the water polo players when compared to the field hockey players? How does knowing the mean absolute deviation help with making observations? Well, first off, we can see that on average, the water polo players are actually taller. I wouldn't have figured that one. I guess that's so they can touch the bottom easier. I don't know, but they're on average about 6 inches taller than the field hockey players. That said, the field hockey players do have a little bit more consistency in their mean absolute deviation, but not much. 1.94 to 2.01. That is pretty dang close when you're comparing the two of them. Now, you have learned to make inferences about two populations by comparing the centers and the variations of the sample distributions. You can also make inferences about how likely it is that the means of the population are similar or different. A local veterinarian, Dr. Gibson, weighed a random sample of male and female adult dogs. The results are shown in the double box plot. Dr. Gibson wants to know how likely is it that the mean weights of the female and the mean weights of the male are going to be different. So Dr. Gibson can informally assess the degree of visual overlap between the two distributions. A visual overlap shows the distance between the two means of distribution as seen in the shaded section of the box plot. So maybe that'll even be our last definition of the year. We'll see. So right here you have a visual overlap where you have a comparison where the data for the females and the data for the males appears overlapping in both graphs. Pretty simple concept right here. Just by looking at the samples of the double box plot or dot plot, how likely are you to think that the population means are different? Well, just taking and looking at it, I'm going to say that overall, males are going to be bigger than females, but they're not always going to be bigger than females. To formally assess the degree of visual overlap, we're going to express the difference of the means as a multiple of a measure of variability. In other words, we're going to find and analyze the ratio of the difference of means when compared to, I hate to say it, the mean absolute deviation. Dang it. All right, let's get into this. This doesn't sound like fun anymore. First thing you're going to do is find the center of variability. So both distributions are going to be symmetric. Since they're going to be symmetric, that means the means and the mean of the mean is going to be the center point. So since we have the center point, now we're going to find the means and we're going to find the mean absolute deviation. So let's get everything loaded here. And now we have that. First we're going to find the means. And on the flip card, the means, if you took all the females, added them up, and divided by the number of numbers, it's going to be 62. But look at this right here. 62. All right, it's the median is going to be the mean because you have a symmetric thing. On the males, if you added them all up and divided by the number of numbers, it's going to be 65. And what do you have right here? 65 is going to be the middle value of the males. So the median and the mean are the same when you're dealing with a symmetrical graph. When we subtract those two means, 65 minus 32, we're going to get a difference of 3 pounds. So Next thing we need to do is find the mean absolute deviation by finding the mean distance of each data value from the mean. Let's look at that. First thing here, you know how to do this. They gave it to us, all right? They found the distance each one of the data values was from the mean, averaged it out, and found a mean absolute deviation of our females of 0.92. Then they did the same thing to the males and found a mean absolute deviation of 1.01. That means you have greater consistency in the weights of the females as compared to the weights of the males. To the nearest whole pound, the variability of mean absolute deviation is a distribution of 1 pound. So they both come out to be about a pound. This means the average distance of each dog's weight is in the sample from the mean or average is going to be 1 pound. The distributions have similar variability, even though they're a little different, they're very close, but they have different means or averages. Now it comes time to plug in the new math that we're learning here. We're going to compare the difference between the means and the mean absolute deviation. So the difference of the means earlier we found was 3. Remember, we subtracted 65 and 62 and got 3. That's the difference of the means. From there, we took that means and divided it by the mean absolute deviation, which they said both of them had a mean absolute deviation of about 1. And when we do that, we ended up getting 3 for our answer. The means, therefore, are separated by a 3-to-1 ratio, otherwise known as 3 mean absolute deviations. Okay? Think about what we're saying here. The difference is 3 pounds. A mean absolute deviation is 1 pound. How many 1 pounds are there in 3 pounds? 3. Therefore, you have a difference. The means is going to be separated on the two of them by 3 mean absolute deviations. Okay? A lot of vocab here. Let's keep going. When the variability is small, such as 1 pound, the data are less separate. When the variability is small, such as 1 pound, the data are less spread out and are more consistent. Okay, everything's clumped there together. Dr. Gibson can have a higher confidence in making an inference that it is likely the means are going to be different, or the averages are going to be different. Because the sample means that the sample means are different, the variability is going to be low. The ratio of the difference in the means compared to the mean absolute deviation takes both of these into account. The greater the ratio, the more likely it is that the means of the populations are going to be different. So 3, you had a ratio of 3-to-1. That's a pretty good gap that says you're going to have a difference in the average weight of these two types of dogs, boys and girls. If you had a ratio of 10-to-1, then you're going to have an even bigger gap between the ratios of the boys and girls. But what if you had a ratio that ended up being 1-to-2 ratio, 0.5, then all of a sudden there's not a whole lot of difference between the size of the weight of the boy and girl dogs. But in this case, going back, it was a 3-to-1 ratio. So let's look at some sample distributions here. First off, the mean absolute deviation is less than 2, then the separation between the samples should be less noticeable, meaning the overlap should be greater, the males and females should be really close to the same weight. However, if your difference between your difference in means and the mean absolute deviation is greater than 2, then that means you have more separation between those two bar graphs. It's more likely to be different. In the ratio we have, where we have a 3-to-1 ratio, 3 is a number that is greater than 2, and because it's greater than 2, we can say that the separation between the samples for males and females is noticeable. The mean weight of the male dogs and the female dogs is likely to be different. Even though there's overlap, it's likely that their weights are going to be different. So let's look at example 1. We only have 2 slides left, or resources left here, guys. The dot plot shows the daily high temperature of the 2 cities from 13 randomly chosen days in July. The table gives the mean and the mean absolute deviation. So you have a mean of 82 and 84 degrees. You have a mean absolute deviation of 1.4. Looking at the 2 dot plots, there's definitely some overlap. Fortunately, we're looking at symmetrical dot plots where you got the centers, or the median is also going to be the mean. That makes it a little bit easier sometimes. How many measures of variation separate the means in the samples? Well, that's going to be 2 and 84, so you're going to be 2 different. The difference in the means is going to be 2. And you can take that, divide that, of course, by the mean absolute deviation of 1.4, and that's how we're going to end up making our inference about whether or not the average temperature in July is likely to be different in each city. So, what do we know? We have this information. We're going to plug in the 84 minus 2, just like I said a minute ago. That gave you 2, divided by the 1.4, and that gave you a 1.43. Now, is 1.43 greater than 2 or less than 2? It is less than 2. And because it is less than 2, we can take and say from there that making our inference is loading. Come on, let's get it done. Using the conventions provided earlier, the ratio that is less than 2 indicates that the means or averages of the population are likely to be the same, because 1.43 is less than 2. It is likely that the average high temperature in July is going to be the same for each city. Check it, and it checks. That's all there is to doing this. The hard part is finding that stinking mean absolute deviation. Don't think there's anything else on this. Let me check. Nope, we're good. It's time to move on to extra example 1. Island Airways and Atana Express are competing airlines. The double plot shows the results of a random samples of flight times in hours for each airline. The table shows the mean and the mean absolute deviation for the flight times of each. Praise heaven, they actually gave us everything we need to solve this. We don't even have to find the mean absolute deviation. How many measures of variability separate the samples, make an inference that compares the mean populations? So I'm going to take and pause this for just a second. I wrote down my formula, the difference in means divided by the mean absolute deviation. The difference in means is, of course, going to be 5 minus 3, which is going to be 2, divided by 0.9. And I'm so happy that we're about done here, I'm even going to use a calculator because I've had enough of you guys. Nothing personal, but hey, we've been together for a year. I'm ready for a fresh batch. But let's get on with this. 2 divided by 0.9 equals a mean absolute deviation of 2.2 repeating. Now let's go back to our textbook and see what options they give us to go from there. All right, find the number of measures of variability. The means of the samples are separated by 2.22 measures of variability. That part's good. And because the answer to part A is greater than 2, it is likely that the means of the 2 populations are going to be different. Check your answers. That's it. We're done. We have answered everything. We have done all the lessons in the entire textbook. The videos are done. Thank you. All right. Now, guys, get busy on this homework assignment. Bring any questions you have to me in class tomorrow.